This is part 5 of our extensive Mosaic tutorial, and we will discuss star color calibration in this part. The data that we are using is courtesy of Stefan Lenz. It's his Milky Way and Rho Ophiuchi mosaic. The data was captured in Namibia at the Kiripotib astrofarm. The star color calibration tool in Astro Pixel Processor has two different models. We have the balance RGB model. This is a very simplistic model which will basically balance red, green and blue in your image. And we have a much more sophisticated model based on real physics, which is called the black body and extinction model. What you will need to do, you will need to select areas in your image where the stars are not strongly influenced by nebulosity. So you need to select star fields without extensive nebulosity. The purpose is to select those stars that represent main sequence stars. That's for the physics behind the calculations. You will need to realize that most of the stars in our images will be main sequence stars that reside in our own galaxy, the Milky Way. So, in all of our images, most of the stars that you see are main sequence stars. Those are stars that are in the first phase of their evolution. And the first phase of the evolution is generally the phase in which each star lives most part of his life. The blackbody and extinction model parameters, slope and constant, depend actually on the used camera and the used filters, either internally and or externally. So those could be filters that reside inside the camera as well. The constant parameters can be used to adjust the calibration for either green or magenta cast. And if you need to lower or raise one of the constants, try to raise them both a similar amount. We also have the blue and red slider in the calibration module. It needs to be used to perform the important white star calibration. Realize in this case that most of the stars from the selected areas must be red stars, since the red stars live much longer than the blue stars. There are simply much more old red stars than there are young blue stars. And this generally holds for star populations in general. That's the physics of stars. Old red stars are low mass stars and therefore live long, and young blue stars are really massive stars and they live much shorter, they have much shorter lifetimes. So, after calibration, most of the stars in your image should normally be orange or red. So, by adjusting the blue-red slider, you are informing Astro Pixel Processor the location of white stars in the selected star population. Finally, adjust the slope parameters in such a way that the star populations in the color diagrams nicely follow the model line. Now, let us start the star color calibration tool. You can find it under 9 tools, calibrate star colors. We are going to load this image into the tool This is our image as produced in the previous part of this tutorial. It is the result of the light pollution and gradient correction as done in part 4. So we load this image into the tool, and the first thing we'll need to do is we will need to select areas in our image with star populations that aren't strongly affected by nebulosity. So in this image I'm going to select this region and this region. This is a nice area, and this part as well. As you can see, I'm selecting areas with lots of stars but not a lot of nebulosity that will affect the star colors. If I select an area like this, obviously the star colors will be affected by the brown dust and reflection nebula in this region. So don't select an area like that. So we have selected our areas, and we will now start a first star color calibration calculation. We are going to use the black body and extinction model because it's much more sophisticated, and we click on calculate. The star color calibration tool will detect and analyze all the stars in our selected regions, and then it will perform a calibration calculation to adjust the star colors. It will then apply the result of the calculation to the actual data, so we will get a preview of the calculation result. The actual data isn't adjusted yet. So this is our first result. As you can see, colors have changed a bit, and the next step will be to fine-tune this result. We see a slight greenish cast. That's the first thing we're going to solve. And we're solving that by adjusting the magenta green constant. The constant will lower the star populations in these diagrams. These diagrams are called color diagrams. Let me first explain a little bit about these graphs. As you can see on the axis, we have on the horizontal axis for both graphs the color, the astronomical color, green minus red. What does this mean? It means that the stars, which are all these dots, if they are more to the right, they are redder, and if they are more to the left, they are greener or bluer. And on the vertical axis, we have, in this case, the color blue minus red, and here we have the astronomical color blue minus green, and in this case it means the same. If we go higher, it means the stars are more red. If we go lower, the stars are more blue. So that is easy for you to remember. And you see these white lines, these are the zero value lines. So basically this would indicate white stars in the star population. These stars will be reddish and these stars will be bluish. So reddish, orange, white, bluish, blue. As I said before, we first want to correct the slight greenish cast that is still apparent in the data, and we're going to use that, do that with the magenta green constants. These constants will have the effect that our model line, which is the green line, as you can see here in the legenda, the black body model, we will lower that line. So by adjusting the constant, we are lowering both these green lines. And as you can see from the values on this axis, if I were to lower it by 0.1, this graph should drop to here. So this line should be dropped 0.1. Let us do that. What we'll do this for both graphs, since these graphs are related. They affect the same star population. All the stars which are shown as dots here are shown here as well in this diagram. So we are going to lower this constant value for both graphs. So the calculation finished, and as you can see, the model line has dropped with a value of 0.1 in both graphs. We can now see this white line. This is drawn always. As you can see in the legenda, that's the default black body model. So this will show you how the model has changed relative to the initial default values of our model. If we look at our image, we can see that the slight greenish cast has reduced a little bit. I think we can still see a little bit. So let's lower it just a tad more and run another calculation. Like in the other tools, if we press calculate now, it isn't affected by our previous calculations. Each time a new model calculation is done based on these parameters and our star population. The star population, however, is remembered. So if you were to select new regions, then all the stars will be detected and analyzed again. But if you don't change the areas that we use, if you don't change the star population, it can immediately start with the calibration routine. So as you can see, this new calculation finished and the green line has dropped a little bit more. Now let's look at our data. I think the greenish cast has been removed. The constant parameters are basically used to either reduce a green cast in your data or a magenta cast. If you were to lower it even more, then we will start to create a magenta cast, which we obviously don't want to do. But if you have a magenta cast, you will need to increase the constants. If you have a green cast, lower the constants. The next step in our calibration of the star colors is to adjust the slope values of both graphs. So this slope value indicates the slope of our green line in this graph, and this slope value indicates this slope. This graph has a higher slope than this graph usually. And you also need to realize that, like for the constant, the slope of both graphs are related to each other. So it's good to keep in mind that if you adjust one of these slopes, adjust the other slope as well with a similar amount in percentages. So if I were to decrease the slope by 10%, decrease this slope 10% as well. Further fine-tuning could be done, but you will need to do that based on how the star population is shown in the graph. Well, the lower graph usually indicates the best, which is a correct slope, and it's important to realize that the slope and constant values, so that basically both parameters determine where this green line is in the graph, those are actually dependent on the used camera and filters in your setup. So if you are using the same setup, you would expect for the end results to have similar slope and constant values in the star color calibration routine. Well, if we look at the star population in our lower graph, it seems that this slope value is slightly off. This is the slope value of 2. It looks like we can reduce it a little bit. Let's lower it 10%, and like I said, lower the other one 10% as well. So I'm reducing this one with a value of 0.2, and I'm reducing this slope with 0.1. And then we click on calculate, and we expect this green line to have a lower slope, and we can actually see that by looking at how the slope from the green line is when compared to the default black body model. So the calculation is complete. The calibration parameters are applied to the data for our preview. And there it is. As you can see from the graph, this green line now has a somewhat lower slope. We can see this here as well. And actually this model line seems to better fit our data in this case. The result on the actual colors that you see for tweaking the slope values are rather minor, but the result is there. Now, we have 2 more sliders that we can adjust in the black body and extinction model. It's a star rejection kappa value and the blue-red slider. Blue-red slider is used for white star calibration, and we'll do that as the last step. The star rejection kappa slider is a control for you to select how many stars of the star population need to be used. If you were to lower this, then less stars from these areas are used for the star color calibration. Normally, you won't need to reduce this to a value lower than 2. And the reason is that from these areas, most of the stars are main sequence stars, and those should be used for the star color calibration. If you have selected areas with clear nebulosity, you might need to change it, but usually this is not necessary. But anyway, this slider, the star rejection kappa slider, gives you a control to select how many stars are used. And these regions in this image contain lots of stars, and probably 99% of those stars are main sequence stars, which we want to use in our calculation. So in this case, I'm going to increase this. If you leave it at 2, it usually means that 95% of the stars are used. If I set it at 3, 99 or even more, 99% or even more stars are used in the calculation. If you look at the graphs, the blue stars, those are the stars that are used in the model calculation, and the orange stars are considered outliers, and so they won't be used for the model calculation. So if I were to calculate now, I expect to see more blue stars in the diagrams and less orange stars. So the calculation finished, and indeed we see a lot more blue stars that are used for the model calculation and less orange stars. These orange stars are probably not main sequence stars, or, which could be another possibility, they might be some stars in our data that have some artifact, perhaps. Maybe there is still a hot pixel or something else going on, but this mechanism ensures that only safe stars are used in our calculation. Let me make a small comment on the star populations that we see in these graphs. So most of the stars are now used for the black body star color calibration. These orange stars aren't used. Well, in most cases these are simply real stars, not affected by artifacts, but they are outliers and not used for the calculation because they are most likely not main sequence stars. So that means these stars are probably in their evolutionary path beyond their main sequence life phase. So these could be red giants, or they could be white dwarfs, dying stars. So that's the explanation why there will always be outliers in your star population. Not all stars are main sequence stars, but there could be red giants and white dwarfs. So you are the population is telling you that that you have perhaps some white dwarfs and red giants in your data as well. So let's focus now on the final calibration step, which is our blue-red slider. And this is our white star calibration. What will do this? Well, what it will do, if I increase this to red, I will be shifting the star population towards red. And in this case it means it will go to the top right side of our diagram. If I were to decrease this slider and push it to the blue side, I will be moving the star population in both graphs to the bottom left corner. Remember, if the stars are more to the right and to the top side of the diagram, they are more red. If they are more to the bottom and to the left side, they are more blue. So, by adjusting this, the place of white stars, which will be over here, we will be shifting where our white star is in our population. So therefore, this controls the white star calibration. And probably it's the easiest way to perform this is by zooming in on some colorful stars or colorful nebulosity and then adjust the blue-red slider. Well, in this case, it's pretty nice to zoom in on this beautiful area and perform the adjustment to see what happens. Well, before doing a first adjustment, let me remind you that most of the stars in our images should be red, because the red stars are low mass stars, they have a low mass and therefore they live long. Higher mass stars will be bluer and have shorter lifetimes. So if you look at stellar statistics, you will see that there are much more red stars than blue stars in star populations. Let's look at our graph. These stars will be red, while these stars will be blue. So in this case, we already have much more red stars than blue stars, as you can see from the diagrams. So that is telling us that we are already pretty good in our star color calibration. Well, what happens if I increase the slider towards red? I expect red to be more dominant over blue. So this could have an effect on this blue nebula. It could probably be more neutral of color or less blue. So let's give it a try. Let's increase it. And this basically is you can see this as a percentage. So we are increasing this by 10%. Click on calculate. We disable the scale to fit, so the next image is shown in this region, so we don't need to zoom in again. So, calculation has been completed. It is being applied to our data for our preview. Let's have a look at the graph. It's coming right now. The new graph. There it is. Well, as you can see, let's look at the data first. Our blue reflection nebula over here, what will happen? Well, as you can see, this has a very strong impact immediately. This blue reflection nebula is almost not visible anymore. So that doesn't look right. And if you look at our graph, basically most of our stars are only white, orange, red, yellow. We have very little blue stars now. So this is probably too much. Let's see what happens. Remember, the default value was 0. Let's put it at minus 10%, minus 0.10. This should actually make this a lot more blue, but will probably have an adverse effect on this red nebulosity. So, the calculation completed. Let's look at our new graph and the 0 values of both axes. And let's see how the star population is with regards to the 0 values. Let's look at our data, how that changes. It's being loaded right now. Well, as you can see, now we have a lot more blue in our data. And let's look at our star population. Now we have little red stars and much more blue stars. Well, and based on physics of stars, that can't be right, because there should be more red stars than blue stars. So probably this is not a good value as well. The best value should be somewhere between -10 and +10. Remember, I showed what happens if I put it at plus 0.1, then we got a 2 red result. Apparently, the middle value already is pretty good. Let's calculate that one again. Here it comes. So this is the data with our default value for blue-red without any adjustment. As you can see, the blue reflection nebula is still visible. The red nebulosity is visible as well. Let's zoom in a little bit more. As you can see, there's even a bit of emission nebulosity over here and over here. And as you can see, the data is very strongly stretched. We are still using a preview with the preview filter as was used in the previous part of this tutorial, in the part where we corrected light pollution and gradients. Perhaps we can reduce the preview filter and make it less aggressive now. I'm going to set this at a lower value. If we stretch very strongly, colors will be a bit more whitish. So therefore I'm reducing it a little bit. This should help me see a little bit more color. As you can see, it does. Well, let's zoom out. So, based on the star population that I see over here, and based on the colors that I see over here, you can see emission nebula in this region, this part as well, over here, even a little bit over here, making this red nebula even a bit magenta, a bit purple, which is correct. This actually looks a very good calibration. If you think the data should be a little bit more blue, lower this to the blue side, click on calculate. If you think it should be more red, increase it to the red side. Let's have a look at all data. Let's zoom in on this part. I think the colors are really great. The nebulosity is shown well. Dust should be brown, which is shown well. We have very nice brown dust, as you can see. So I think this concludes star color calibration. And we'll stop the tool by clicking on OK and save. And we will save this again as a FITS file. It's linear data still. And the next part in this tutorial will be final adjustments with the selective color tool and some explanation about how to use the preview filter. Finally, to conclude the star color calibration tutorial, let me show you in one image the difference between the uncalibrated and the star color calibrated results. At the top you see the result from which we started. That was the data that was corrected for gradients and light pollution in part 4 of the tutorial. and at the bottom you see our calibrated result. Clearly the differences are big. You can see the green cast has been reduced in the initial data. You can see that color is preserved as well. You can see that the Milky Way is whitish to yellowish, which we expect. And we know from our star color calibration result that there are more red than blue stars. Zooming in on this region like we did in the tutorial showed us that we have a very nice colorful calibration result.